You hear now? Okay. This is better. Okay, let's do the laptop.
Yeah, first. Okay, is it working? Can you confirm that it's louder? Doesn't seem like it.
The chat.
This is much better. Okay. Okay, yeah, then sorry, let's restart maybe. Okay, yeah, the paper I wanted to talk about is recount fusion, 3D reconstruction with diffusion priors. It's a recent preprint, and the task they tackle is single scene reconstruction. So like the general nerve setting, and mainly also like focusing on sparse view reconstruction. And what they want to investigate is how can you like reduce the number of the views, like because capturing like a nerve is really like expensive. You need a lot of views. How can you replace basically maybe views with 3D diffusion priors? Like maybe one related work which was proposed, also presented here recently, was the Zero NVS, which also tackles like a similar task, that you use some sort of diffusion prior here with like an SDS kind of loss to fill in the missing views. And about their method, what they do, they don't use any SDS kind of loss, but what they do is like on the left, you can see the general nerve settings. So you have like a given number of input views. And for these input views, you use the normal like reconstruction loss. But what you also do during training, you sample random views, not totally random, but kind of like the views in between, and use for these views, as you don't have like any ground truth images to reconstruct, you use like the diffusion prior to reconstruct in these from these views. And how this works is basically, you can see on the right, this is like the diffusion prior. So you sample like a random view from the nerve on the left. Then you encode it with, in this case, this is like a latent diffusion model. You encode it, and then you add a given amount of noise to the encoded image. Then you let it denoise with a given number of steps, decode it with the decoder of the latent diffusion model, and then basically have some sort of loss or gradient you can backpropagate to the nerve representation, basically. This is not exactly like the SDS kind of approach, where you add basically a noise and do a single step with the diffusion network, but it's like a multi-step approach. So you add like a given number of noise, which is not necessarily for one step. And in their case, they used 10 steps. And then you perform like 10 steps of the denoising operation, and then decode it. And then basically through this, you have an additional loss for the views which are not part of the training data set. And as a detail, what they do on top of inputting to the denoising unit, they don't only input the encoded latent feature of the image, but also what they do is that they use like a pixel nerve to input a given number of input views. Like in this case, they basically take the closest views to the random view and encode them basically with a pixel nerve. And through this, they have some sort of like 3D encoded like features, which they basically concatenate on top of the features from the target view. And what they also do is they encode the clip into clip. They encode the input images of the training set into clip embeddings, image embeddings, and also feed them to the denoising unit. And basically with this, they can fill in like the missing holes or like the missing views and better reconstruct scenes, and also like reconstruct them much better with in the sparse view setting. So I would say most of these methods are already explored, but it's kind of like putting all this together is kind of like and providing this quality is probably the novel part of this method. Maybe to note that this denoising UNet was pre-trained on like image data first, and then it was fine-tuned on a given like on 4 or 5 like 3D data sets. So it's like kind of a mixture of data sets, how this denoising UNet was trained to be 3D aware basically. And yeah, similar with this pixel nerf. So this was like, it was first pre-trained like as a only as a 2D model, but then fine-tuned on 3D data. About the results, so they compare on like various data sets, mainly against like these. They compared also to like ZipNerf, which they build up on basically, which is like the state-of-the-art nerf for like dense views. But they also compare mainly to all these sparse view reconstruction methods. And they show basically on different data sets that they can reconstruct like also complex scenes much better than previous works.
Was it just a regular F2 loss or added ones?
This one?
Yeah.
Yeah, basically, yeah. It's like
The diffusion model not to like random detail artifacts or something like that. Like, why is it always consistent with that object?
I mean, it's not like an L2 loss. It's kind of a mix between like some sort of SDS loss, but it's not exactly SDS, because in SDS you only add noise for a single step and then denoise it. It's kind of like a mix between what InstructNerf to Nerf does with like these data set updates, but formulated more in a SDS type of setting. So I would say it doesn't provide like a reconstruction loss. It's like they call it sampling loss. It's kind of a I think this was explored at some previous work, I think Sparse Fusion or something, where they do also multi-step.
The loss is in like RGB images or on the noise?
It's on the RGB images. So these two are basically compared. You have basically, in the end, you have to consistently only through the nerf, basically.
Do they show any failure cases?
Yeah, maybe we first look at the ablations. So at the top you can see, so pose here means instead of using, so they use pixel nerf, but basically can encode like multiple views and then averages out the features basically of these multiple views. But what you can also like do as a more naive setting, or like simpler setting, what like 0, 1, 2, 3 and these methods do is only condition on the image and the camera matrices instead of having like an actual like rendering of the features. So this means pose basically. If you replace the pixel nerf with just like extrinsics and image conditioning, and you can see that if you compare to ours, that like this approach seems to work much better. And also this ablation without PT means so this diffusion model, it was pre-trained on image data, so on 2D image data, and this seems also to be quite important to pre-train it first, to have like some sort of more broader like big data and broader knowledge about image distributions in general. Here they also compare to SDS. So you can see, especially here on this, like where this thing is on, like that it blends in with like the table basically. And so they have like two different, so their multi-step approach, they have two variants, like the vanilla multi-step, and here where they anneal like the time steps where they, for the diffusion model, which time steps they're sampling from. And you can see that, yeah, mainly this proposed method doesn't look much better, but it looks better, I would say, than, especially, yeah, the background is less blurry, and this thing here is doesn't blend in with the table. Yeah, maybe we go on their website to see the results.
So their diffusion model was stable diffusion?
It wasn't exactly stable diffusion. So they trained like an architecture like stable diffusion, like latent diffusion, what stable diffusion used, but they pre-trained it on like some internal image data set, but I would say it's comparable to stable diffusion probably.
And was it multi-view data, or was it?
So it was first trained on single view data and then was fine-tuned on like a bunch of multi-view data. How can I remove? And it was fine-tuned on like, let me see which data sets it was again, but it was like a mixture of like five multi-view data sets or something, like the regular ones, like observers, real estate. Let me see. Training data was Co3D, MV ImageNet, real estate. Okay, it wasn't actually so many. Oh, here also observers. So it's like, yeah, there's one synthetic and 3 real-world 3D data sets.
Did they discuss how long it takes to train?
No, they didn't say anything about training or compute. I would say, yeah, just training this diffusion model takes a long time. No, they didn't say anything. Yeah. But let's maybe first look at the results. So you can see like, yeah, that compared, oh, you can't see even what is here. So this is their method, and this is ZipNerf. So ZipNerf is basically just a naive, like designed for dense view reconstruction. So it doesn't do well in the views in between, and Reconfusionist basically can help to fill in the missing views with this diffusion prior.
I have another question. So how many views do they augment with? Like, is it only views that are close? And like how many?
So for the views which are used with the diffusion prior, they define it like, they define like a trajectory of a camera, which depends, like, so basically you don't want to sample like random views because it might be within like an object or something where density is. So you define like, they didn't very specify how they define this camera trajectory, but it's like basically probably based on where density might be or something. And then you can like, you sample on this trajectory randomly some sort of the views. So it's not everywhere sampled for the diffusion price, but like on some predefined trajectory.
So I have a question.
Yeah.
I'm not really familiar with PixelNerf. What type of results do you have?
So PixelNerf is mainly like, I would say it's the main method, or like it's an older method, but still like state of the art for like, if you have sparse views and you want to where's the method here basically. So what it does is just like you have like you encode basically your view with like here CNN encoder. They also use a CNN encoder into some like feature volume, and then you can render the feature volume from like a target view, and then has basically based on like your input view. Also, this is just a single view they show, but you can imagine this feature volume can be computed from multiple views. Like you encode multiple views into like a volume, and then you can average, like compute a mean across like the number of views, and then you have some sort of feature volume like representation, which you can then render from your target view from new views. And
Right, so for this, for rendering, they also need to use a decoder, right? So it's like you have a feature volume and then the rendering, you need to pass that through some decoder, right?
So for this, you need like you have basically here like in Pixel Nerf, you have like a normal Nerf MLP decoding to RGB and density, but like in this setting, what you have, yeah, you use basically the rendered features directly instead of decoding them into like with some volume rendering pipeline. You just use like, so you have multiple views here, let's say 3 views. You encode these 3 views with Pixel Nerf into a feature volume, and then you render it from your target view, and then basically have, the main idea is to use like nearby views. Instead of just using the diffusion loss for this new view, you also use like nearby actual input views from your data set to give it more like guidance basically from the real data set. So I would say this is not only, it's kind of maybe misleading, it's not only diffusion for the missing views, but it's like a combination of using a pre-trained denoising unit, like a pre-trained diffusion prior plus a few input views which are encoded by Pixel Nerf and the clip embedding. So it's like a mixture here, and this is just a regular Nerf training basically.
Yeah. So conceptually, compared to SDS, it's like they have better gradient and they are taking larger steps.
Yeah. Yeah, I mean, SDS doesn't use all this part, like they don't do. So this like was actually similarly used in GenVS, which is like also like a few view reconstruction method. So many methods actually use Pixel Nerf to encode, like if you have if you do autoregressive sampling or these kind of techniques, when you have already a few views and want to generate a new view, like it's very common to use like this kind of embedded features. But yeah, I would say the comparison to SDS is mainly this, on top of that they condition on more stuff, they also do like, this multi-step denoising basically. And maybe to look into more results, you can see here also, generally you have like with this dense view reconstruction, like here you can see in ZipNerf a lot of floaters, a lot of like wrong density, because like you don't have any knowledge about these views. And then basically you can see this method as the diffusion prior just cleans up all these floaters and wrong densities. I would say this looks pretty clean, and it's generally the method isn't super novel, and the authors also acknowledge that it's like there's nothing novel in the pipeline. It's more like putting the things together into one pipeline and investigating it. Like what they also do like is it doesn't only work on like sparse views, so it doesn't only help on sparse views. Like I would say it probably will converge to a common point at some point if it goes really dense, but even like for 81 views, it's still like it boosts like the quality.
So maybe a bit better because it's like all the flat textures and stuff that Nerf doesn't know what to do. But diffusion will tell it, for example, a table is supposed to be flat. So.
Yeah. Okay. Any more questions?
Hey. Yeah, hey Sherry. Can you hear me?
Yeah.
Cool. Yeah, small question like about pre-training. So they pre-train on multi-view data set only. Can they use like just stable diffusion that is pre-trained only on images without like 3D stuff, like without these multi-view data sets?
So they first pre-train it on like image data, and then they fine-tune it basically on the 3D data to make it let me check here if they have actually some ablation for it. Sorry, 1 second. Yeah, I think their main motivation, they didn't do like an ablation, but they're saying basically, if you'd only train it on 2D data, it's kind of, I think it's probably not super stable. Like it's, the images are consistent and everything. And probably they had more floaters and this kind of stuff without actually fine-tuning it on 3D data. So I would say it probably helps like to remove the floaters, have it more 3D aware. It's kind of similar to why like these methods like MVDream for text to 3D generation fine-tune on 3D data. So I would say similar reason, but they didn't provide like any comparison, I think, with only 2D data, how it would work there.
Don't use the camera.
Not in their pipeline afterwards, I think. I mean, you have like
sorry, yeah, go ahead.
yeah, go ahead.
Just question about Pixel Nerve. So Pixel Nerve is also pre-trained on multi-view data. So the whole pipeline is fine-tuned on the multi-view data set, like Project Pixel Nerve.
This is trained like end to end, like the Pixel Nerve. Like it's trained as part of this. So the diffusion model is pre-trained, and if I remember correctly, Pixel Nerve was trained end to end with for the single scene basically.
Okay. Okay, yeah, thank you.
Yeah. Without any unpost feature ending instead of why not? They don't evaluate like Pixel Nerve to respond to the question of Jay. They don't evaluate without and like unpost features because like yeah, I think if you don't have the poses of these images, then you couldn't do this whole part. So I mean these poses like you require to know somewhat like that you have like the input images and their poses somewhat given. So but for the 3D data, I think this is mainly used to train like the diffusion prior basically on 3D data. So it's some sort of 3D aware. Yeah, the Pixel Nerve is mainly done like to incorporate the input images which you already have into the diffusion prior. So it's yeah. Okay, yeah, maybe we move on to the next paper.
Thank you. Okay. So next paper is next paper is Splat TAM. So this is Splat Track and Map 3D Gaussians for dense RGBD SLAM. And okay, so the goal here is to get a sequence of RGBD images in real time and output a 3D reconstruction of the scene. That means that you have to estimate color, geometry, and camera extrinsic parameters all together. This problem is called classically SLAM, and it's different from traditional NeRFs or Gaussian splats because you don't have the camera parameters, but you also have the depth as input. Okay, so the overview of the method is that they have 3 stages. At each time, think that you are, okay, so their preferred way of showing scenes is Gaussian splats. And at each time step t-1, think that you already have a Gaussian splatting reconstruction of a part of the scene and you get a new frame with its RGB and depth. And you do 3 steps to update your scene. First, you have to understand the camera parameters of the incoming frame. So first they estimate the camera parameters. After that, they can now use the depth values of the input RGBD image to unproject some of the points on the input image to get some new Gaussians. This part is called Gaussian densification. And at the end, they freeze the camera parameters and just optimize the new Gaussians that they have added to match the new image that they have received. So I will go into details of each of these steps. So the representation is a 3D Gaussian splat, and they don't use the original Gaussian splatting. They simplify it so it doesn't have view-dependent colors, and the Gaussians are isotropic. So here's the simplified version of the splatting process. So f of x is just the opacity here, which is now just a isotropic Gaussian PDF, and then the splatting to the 2D mean and the radius is just simplified to these equations. Now, for the first stage, they want to find the camera parameters. So getting a frame from a time t+1, they render 3 things based on their current model. They render depth similar to color, and this is just the volume rendering formula in Gaussian splats, and same as NeRF. So they have color or depth at each Gaussian that has been projected to the 2D or splat, and they order them so that the closest one is the first in the queue, and the farthest one in depth is the last in the queue, and then they do this alpha blending based on the opacity and the transmittance for both color and depth. And the depth is just the depth of the mean point. And they also render the silhouette, which is just the alpha value, the opacity of each pixel. And then to optimize the camera parameter of the new new frame that they got, they will optimize this loss. So basically for just the silhouettes, just for the pixels that their silhouette is already bigger than 0.99, which means we already have a good estimate of these parts of the image based on our previous model. They try to minimize the depth loss and the the color loss, and find the camera extrinsics. So their camera intrinsics are not predicted here, and they assume that it's given for one camera. So they also don't start from a random initialization. So for the first incoming image, they use an identity matrix for the camera extrinsics, but for the next frames, they assume that there's a constant velocity, and they can set that velocity to whatever they want. For example, one way you can initialize it is just the difference between the last frame and the frame before that. Okay, so after they have the camera parameters, they do the Gaussian densification process, which is they look at the parts of the scene that are relatively parts of the image that are relatively empty according to the previous model. So that's the parts that have a silhouette of less than 0.5, and they unproject some of the pixels in the incoming image using the depth and the known camera parameters to get new means for new Gaussians, and set their color to the pixel color and the radius so that its radius would be equal to 1 when it's projected back onto that image. That would be the grand truth depth that they get from the RGBD image divided by the focal length. And as I said, they just do this on the parts that are relatively empty. So their silhouette is less than 0.5.
or the parts that are saying that that might indicate that there's a new geometry in front of the existing geometry, and they show that by parts that have a depth incoming that have a depth in the incoming image less than the current depth, and their error would be more than 50 times the median depth error. So that means that this difference in depth is not because of the error, but it's actually a new geometry in front of the previously found geometry. So if it falls into this mask, they will unproject the pixel and set a new Gaussian. So for the last stage, they have to optimize these new Gaussians to fit the actual image that they got, the new image that they got. So they opted actually all the Gaussians together by optimizing the depth and color loss that we saw here again, but they freeze the camera parameters now. And they only use the k-nearest frames to this frame that they just got in their optimization, so their batch size doesn't get too big. And the nearest frames are the ones that when you project these pixels, these pixels on projected points will fall into the frustums of those cameras. So the more points in the camera frustum, the nearer that frame is to the current frame. And they have some quantitative results. So here they show their, so like previous SLAM-based methods were mostly like point-based. So this is a point cloud-based representation, and ORB SLAM is just a follow-up on this point SLAM. And they show it on like 3 different data sets shown here. The metrics, I think, is like the difference in trajectory in centimeter. And these are the different like scenes. And they show that they work very well in ScanNet++ and Replica. Replica is a synthetic scene, and ScanNet++ is a new version of ScanNet where they captured the scenes mostly for nerf scenes. So they have one very slow capture without any blur, and another capture with another trajectory for test set. While this original ScanNet and this TUM RGBD, they only have one trajectory. So you cannot get like a separate test trajectory for your SLAM setting. They say they don't work very well in this original ScanNet and the other one, TUM RGBD, because their captures are very like have motion blur and have a lot of sparsity in their depth maps. So their method kind of fails. But on these like ScanNet and Replica, they perform very well, much better than the other two. And they say they only can apply their method effectively to when you have dense depth maps. And also they show like PSNR and like image quality metrics. Again, they perform very well compared to like point SLAM and some other SLAM systems based on voxels. And another important thing was their runtime, which is like real time. So you can capture nerfs or Gaussian splats real time with this. And this splat S is when you use half resolution for the Gaussian densification part. So here, instead of projecting all the pixel, you project half of it. And that's very fast and also relatively good in terms of like trajectory error. Yeah, and I think the main reason that this can be done, and the author said that this can be done on Gaussian splats and couldn't be done in NeRFs and was very hard in NeRF, was two things. One, this is like very fast for rendering, so you can do it in real time, the optimization. And the second thing was that your gradients have like a very direct path from the render to the cameras, as opposed to NeRF that it went through like an MLP and many non-linearities. So let's see some of the results. Yeah, so this is done real time, which is very impressive. Same here. You see the geometry is much better in the splat time. And the depth maps are nearly perfect, which is surprising, maybe. Because Gaussian splatting doesn't have a very good depth map, but because they have depth supervision, they get good depth maps too. So their geometry is much better than like regular Gaussian splat. And yeah, that was all. Any questions?
So about the isotropic Gaussian, is there any like noticeable thing because of their pixelat and it's actually as good as
I don't think so, because we saw that in another work too. So I guess it was 4K 4D. They also use isotropic Gaussians, and that also was very high resolution. But it's, yeah, you can see maybe some things because, well, not by eye in the examples that they provided, but in the metrics you can see like the not here, like the PSNRs are like 20 something. Most of the times it's like 30 something, so maybe that's why. But they also don't have camera parameters, so you can't really compare like this. But nothing that I could see in like their qualitative results. It's pretty good. Yeah, they also have depth, so yeah. Anything else?
Yeah, small question, really. So is it correct that this works very good on like almost static scenes, like that are really well captured? So it's not like real, like capturing from the phone and stuff. So it's really like in good setups, it works good.
Yeah, they show it here. Basically, Replica is completely synthetic, and ScanNet is like captured to perfection. So it's not like someone's taking a video casually. ScanNet has very high quality images, no motion blur, and all the depth maps are very dense and don't have any like loss in them, loss of information. While like original ScanNet has like many holes in the depth map. So definitely you cannot just, I guess, take your camera and use this as they show here. They're not performing very well on the original ScanNet, which I would say is the closest to what a person would just, when you just take a video, what happens is like very close to original ScanNet. Yeah. So it works very well on that you are very slow capturing the scene, or it's synthetic.
Yep, thank you.
Like from Mark in the chat. Is it
Yeah.
the author of the paper?
Jay? I don't think so. You- Is he the author? I don't think so. Are you the author, Jay?
Seems like it.
Yeah. For some reason. Oh, they're the author. I didn't know the author. Okay, so they answer our main motivation to use isotropic Gaussians and not use view dependent was primarily optimization and quicker code development and coordinate transforms.
Easier for me to.
Yeah. Yeah, Jade, please let me know next time when I'm presenting your papers. So I usually ask the authors themselves to present. Sorry, I didn't recognize that this was your work sooner. Okay, great. So I think we're done. See you next time.
Thank you.
All right, thank you.